Welcome back. I'm Prof. Watson, and I'm recording the Precap video for the class that we just did on multivariate linear regression. And we introduced the concept of principal component analysis. So this is an interesting class where we talk about the kind of vector spaces that relate the ideas of data to building models for data to all of these kind of cool matrix transforms. And I'm joined today by Asma and Augustin, who had excellent questions, sticking around after class to talk a little bit. So Asma, do you want to ask your core question about PCA again? I thought it was really well phrased. Awesome. Okay. So the core idea of PCA is we're going to start with this matrix where we have the variance of X and covariance of X and Y. And variance of Y. Right. So we start out with, we can compute this matrix from data, right? Does that make sense so far? So this is kind of we have a bunch of data in a space. I'm just looking at the two-dimensional case here, which is kind of silly, but it's also, much easier to visualize. So we have a bunch of data that's distributed in space like this. And from this data, we can compute the variance in each dimension. It's X, it's Y. Here would be our variance. Right. That goes on the diagonal here. And then the covariance, which is just how collinear they are, how much they are. We have a value that's proportional to how much those values move together. And in this case, I've drawn data that's, has a very high covariance. Right. So the data tends to be in this sort of potato shape where large values of X's result in large values of Y and small values of X's result in small values. Tend to have small values of Y. Okay. So using that, we can write down this covariance matrix. So we can compute these values on this matrix. So the thing we then want to do is we want to say, okay, I would like, there are a couple of ways to talk about this. One way, the way that I think is most often taught is, okay, we are going to factor this matrix. We're going to do matrix factorization. This matrix is essentially a system of equations, right? With two unknowns and two equations. And so you could solve for what X and Y were, right? And then that will tell you what X is and Y is, right? By factoring around this matrix, right? It's just like, if we just draw a thing here and say X and Y, we say, okay, so there is some matrix of values here, some transform that we can apply to X and Y that when we apply it to X and Y, when we apply it to every vector, to every XY vector that we have here, we get this data, this cloud data, right? That's one thing to do. And you could factor that matrix and you could get it so that you factor out the covariance. So you just have, you refactor it here. So you'd have a single value for X and a single value for Y in this matrix. That's singular value decomposition, right? And you say, okay, so now I've gotten all of the correlation or the covariance in this case, but the covariance of this out of the matrix. I've taken all the X's and I've characterized them with a single value, all the Y characterized with a single value. So now I have decomposed every one of these data points into two orthogonal vectors that no longer have any angle incident on each other, right? And once I've done that, now I can draw a new set of axes, one that runs along the axis, this new axis of variance, this new X-axis of variance, and this new Y-axis. And turns out that those two axes of variance will look like this, right? So here's this new, so this is our new X-axis of variance from this direction. Right. This is my Y-axis of variance. Right. So this here is called an eigenvector. Each of these is the eigenvector, and these eigenvalues, the largest number here, it looks like this eigenvalue is the larger of the two. So that'd be the first principal component. This purple value is the second principal component. It's the second largest eigenvalue. Right. So that's the transform that you do. If you factor the matrices you're used to from linear algebra, you would get this, right? You ask, geometrically, how should I interpret this? What should be going on in my head so that I'm thinking of this? Okay. So the way that I would think about this is, okay, what an eigenvalue is, or what an eigenvector is a vector in a space that when you apply a transform to the space, that vector does not stretch that the magnitude of that vector can change, right? but it doesn't stretch or skew, right? So it is preserved. That vector is preserved in the rotation space. A great example of this is, this red vector, I could rotate it down. That's a transform that doesn't change this vector. So if you think of this covariance matrix as a transform, right? You're saying, what are the vectors that when I apply this transform to them do not change except in their direction, right? So you're not changing the shape of this vector, you're just changing the direction, right? How big are they? That's their eigenvalue. And what is the vector? That's the eigenvector, right? What direction did they plot? How big are they? That's the eigen. So you try to find the eigenvectors of the space. So geometrically, you say there must exist some vectors out there in the universe, in this universe of data, that corresponds to these eigenvectors, these vectors that don't change when I apply this rotation, when I apply this covariance matrix as I want to them, right? And factoring the matrix solves for those eigenvectors, right? You could do it, I always say, think about it visually. Think about like looking at the thing. You could say like, okay, I see which vectors aren't going to change when I rotate this, right? Those are the ones I'm trying to find when I apply this covariance transform. This covariance transform, remember, is that thing that put these vectors, these XY vectors here in the first place, right? It's the thing that when multiplied by all those XY values, they land right on this spot in the two nucleus. So you're solving for these eigenvectors by factoring this matrix. Does that answer your geometric question? That's okay. Awesome. So that is what I'm going for when I talk about like intuitions that you should have, right? So all of these things mean the same things. Factoring this matrix is a way of finding the eigenvectors of it. Eigenvectors of it are those vectors that do not change except in their direction when you apply this transform. This transform is the covariance matrix represents a kind of transform that you could do to this data that would map it to this space. By using by saying, okay, so if I take these new vectors and I apply them to my old XY data points, X1, X in, Y in, right? So if I multiply these new ones, I can get factor loadings, which map these data points, which transform these data points into this new space. And what I've done then is I've kind of created this new dimensionality where this is my new X-axis. It's the eigenvector in X. It's the largest eigenvector, largest eigenvalue, largest eigenvector. This is my new Y dimension, right? And now all of my, this is this data point right here. And so when I applied this transform to it, what it did was it moved it basically, kind of 45-degree rotation down like that. Now that's going to change the point that X and Y lands on with respect to these new vectors, but that's just fine. So now we've got it here, we've got it here, we've got it here, we've got it here. So now every X and Y value has new values. And we usually call these like the factor loadings, like how much they load on these axes. So we map them to this. Now we're measuring them with respect to these two axes, right? So here's this new vector that points to this data point. So when we have a ledger, we usually just erase the half points, but we still think of it as a vector. And so we've now mapped this vector as this new set of axes. And with those new loadings, we have a way of describing it in this new space. Right. So we're just doing this transform. We just rotate the data. It's an alt vector surface, or we're just rotating it into this space. But now we have a way of talking about with respect to these new axes. We can just, by multiplying by our transform up here, we can map it back into the old space. So if we want to put it back in XY space, no problem. Just multiply it by this transform up here. They pop back into their own space. And that, if we need to reverse the transform, but we can also fit models on the data in this space. And very often it will be easier to fit models on the data in the space. That's kind of where we're going. I gave the example in class, the extreme case where you have very, very high dimensional data, like images, where models are virtually impossible to fit because doing the estimate in all these, super high dimensional cases is very, very complex. But if you map it down to a lower dimensional manifold, it's pretty easy. In fact, this is how image compression very often works. Image compression doesn't use, I think JPEG uses wavelength transforms rather than PCA, but when you transform images into PCA space, you'll get often a smaller file because it is matching. So you can, especially if you ignore the PCA is lossless, you have to discard some of the variations. So you discard the smaller eigenvalues, and then you'll lose some of the resolution at the end. And it'll often lose it in funny ways. You'll actually see this when you do the pre-class work for next class, where you fashion this to data. You lose some funny. Your shirts will start looking funny after you've worked out some of the lower eigenvalues. But the image compression like JPEG uses a different transform, a different structure preserving transform. That is, when you take off the last components of it, it just gets fuzzier rather than getting odd. And you'll see what I mean by that when you get kind of the either shirts. But that's the basic intuitions about things. I think it's a really critical technique to understand because dimensionality reduction is like the rule of thumb for most machine learning professors is at some point they'll tell you, just use PCA on it before you train your model. PCA always works. That's not actually true, but it's true often enough that it's a good rule of thumb. Great. I'll see you guys on Thursday.